Hello, good morning everybody. So, we were talking about some important nitrogen compounds which are industrially important, and one such compound we have seen that is chloramine. And as we see that the chloramine structure is this one, not the hydroxylamine, because hydroxylamine we will talk also along with this. So, if we consider a typical 3 nitrogen hydrogen bond bearing ammonia, that means your NH3, that we all know very well that from ammonia, if we are able to substitute one of the NH bond by NCl bond, we will get the compound which is known as the chloramine. Because this is a very important compound where we have already functionalized like our typical organic chemistry thing, that we have substituted this NH bond by NCl bond, and as we all know that this particular NCl bond will be very much reactive in nature. And if we go for all these reactions, already we have seen that the production of hydrogen also can go through this particular pathway, that means producing chloramine, that means substituting one of the NH bond by NCl, and then again further you can react it with the free ammonia molecule. So, how good this particular molecule is, that we should know, particularly that particular compound, that means chloramine, which is a very unstable compound, that means at a very low temperature and in a very dilute condition, because whenever some compound is explosive in nature, we should go for stabilizing that particular compound. It can also be a gaseous one like your hydrogen. What we have seen that hydrogen can be very well stored in a dilute solution and in presence of water, that is why we get the hydrogen hydrate. Similarly, this chloramine is also a unstable compound because it is highly reactive. Why we consider some compound as unstable? Because it is highly reactive also. So, when we consider that high reaction or high level of reactivity of that particular compound, we can consider that it can immediately react with moisture, air, or any other readily available chemical reagent. What we all know that from atmosphere it can react with some of the gaseous molecules. Similarly, if the compound is present in a solution, then it can be very much reactive with the water as well as some other species which may or may not present in the water medium. So, it is a violently explosive compound. So, is usually handled therefore in a dilute solution. That means a dilute solutions of this chloramine in water or in ether is available as a chemical reagent also. So, laboratory available chemical reagents like these, that means the chloramine can also be available in terms of its solution in water or in terms of its solution in ether, and which can be bottled in a nicer way. That means diethyl ether containing chloramine or the corresponding hydrate of its chloramine. And in terms of its reactivity pattern, when this particular compound, that means NH2Cl, the reaction of NH2Cl would be very much interesting, particularly for the production of 1,1-dimethyl hydrogen, which is well known that it can go for a controlled oxidation process in presence of air or in presence of excess supply of O2. That means O2, that means oxygen from that cylinder as a gas. So, which can be very quickly burnt away, but the substitution from one end of the hydrogen is your NH2. So, substitution from one end basically, that means that particular end, that means the one NH2 end is getting stabilized by making it as an Me2. So, if we can go for stabilizing this particular part by converting NH2 species as an Me2, it is little bit stabilized compared to your free hydrogen. So, it can be used for controlled burning process, that means it can be used for a fuel, because controlled burning of any material give us its character as a fuel. So, this can be very easily prepared. How we can prepare? Because previously we have seen that hydrogen we can prepare from the reaction of chloramine with ammonia, that means NH2Cl plus NH3 is a very simple reaction giving rise to your hydrogen plus HCl. Similarly, if we go for a reaction with this particular amine, is an organic amine now. When we go for a typical substitution of ammonia molecule by methyl, 1-methyl, which is your methylamine, and 2 of the NH groups we can substitute by 2 of these methyl groups, giving you the corresponding dimethylamine compound. So, this dimethylamine compound, if it is allowed to react with your chloramine, it can give you the corresponding 1,1 dimethyl hydrogen molecule. That hydrogen molecule is a very useful rocket fuel also, and definitely since we are using as a rocket fuel, it should be a costlier one. So, production of this particular molecule will be an interesting one. Only thing that how cheaply we can produce and how safely we can produce, because it had some hazard also, the related hazard related to this particular molecule making is also should be considered. So, that way if we go from this particular NH3 to NH2Cl, now if we substitute one of that same NH function by NOH, that means we are getting NH2OH, which we all know from our school days, that is known as your hydroxylamine, because hydroxylamine is a very useful compound for our laboratory purpose also, because it can give you a very useful reaction with that of your aldehyde or ketone, forming the corresponding oximes. And oximes are also industrially important, that we will see. So, it can be considered, this hydroxylamine can be considered as a very useful starting material for some industrial purpose, like that of our making some oximes, and those oximes can be industrially also important, that we will see. So, now how we can get this particular hydroxylamine? So, this hydroxylamine what we will get basically is our thing, that how we can prepare this NH2OH. So, different production routes or different synthetic routes or different preparatory routes are available for hydroxylamine, and it can be handled as salts, because again the consideration of your stabilization, like your hydrogen, we consider hydrogen as the corresponding hydrogen hydrate. Similarly, since this is a basic compound, it can be stabilized at a corresponding sulfate salt, that means it is protonated and then its corresponding anion, if it is available as sulfate, we get the hydrogen sulfate. Like hydroxylamine, hydrochloride or hydroxylamine bisulfate, similar to these, all these, and in aqueous solution to keep yourself away from its reactivity, that means its dangerous attitude for this particular reaction. So, one such reaction, if we consider that if we take the very basic reaction, instead of taking ammonia, now we can go for NO, the nitric oxide, because there are a large number of oxides and we are not able to cover all these in detail in this particular class, because the intended course is huge one, because we will only go for some of the very interesting and very useful molecules only. So, nitrogen oxide preparation is a very, again, a school days preparative stuff, but industrially these are also important. So, how we immediately go for that particular conversion? So, we can have this, that means NO we have only addition of hydrogen only. What is the difference between this NO and NH2? This is, you can compare by addition of 3 hydrogen atoms. So, those hydrogen atoms, if we can transfer to the nitric oxide molecule NO in +2 oxidation state of nitrogen, we get the corresponding hydroxylamine sulfate. So, hydroxylamine sulfate, the formula of that particular compound is NH3OH whole 2 SO4. So, this particular hydroxylamine sulfate can also be obtained for this particular hydrogenation reaction, if we consider hydrogenation reaction in presence of sulfuric acid, which is providing the corresponding sulfate anion as the corresponding anion of that particular salt, which can be isolated from the reaction medium, from the reactor, whatever it is. So, this particular hydrogenation reaction is not a straight cut hydrogenation reaction, and it should be also in catalytic in nature. So, if we can have the catalytic nature of this particular compound, we can go for some optimization of the temperature, optimization of your pressure for the typical use of your hydrogen. This hydrogen is not an typical 1 atmospheric pressure. It should be pressurized from the cylinder or some other source also. So, if we can have, so platinum would be therefore a good catalyst. If we just simply this reaction scheme that tells us that platinum will be a useful catalyst, but we are taking it as a platinized charcoal catalyst. What is that? That you can have a base, that means the charcoal powder or charcoal dust if we get it. So, you can have the corresponding carbon surface. Nowadays we consider as the carbon particles, that different types of different carbon particles, the nanoparticles of carbons are also nowadays available in the market. Before that we can have the simple charcoal powder. So, charcoal powder you can have, and on the charcoal bed if we can have the platinum in the metallic form, not any other form, the platinum metal itself. So, if your charcoal surface is completely covered with the platinum metal powder, we can consider it as a platinized charcoal catalyst, and that platinized charcoal, because we are increasing the corresponding surface area of that particular platinum, and that platinum will be responsible for corresponding hydride formation or in some weak form the hydrogen atom absorption. So, hydrogen atom absorption or the corresponding hydride formation on the platinum will be useful for transferring that hydrogen atoms to your NO molecule, and that transfer of hydrogen we consider as a typical hydrogenation process, and that hydrogenation process will be useful for making or converting your nitric oxide molecule to NH2OH, your hydroxylamine. So, this hydroxylamine and if we are consuming a large amount, say 95% of your production, that means industrial production of hydroxylamine, how good it is for the different purposes. So, more than 97% of its production is utilized for the production of caprolactam. Is an industrially important compound that we also see for making the nylon or polythene making thing. That means it has a typical lactam ring. So, as I told you just now that you can have oxime from hydroxylamine reacting with your ketone or aldehyde. So, that particular one, if we can convert it to a typical caprolactam, and that caprolactam can be useful for making your nylon. So, this particular course is therefore very important in understanding that if I ask you that how nylon is dependent on industrial inorganic chemistry, you can have a very simple answer from there. Okay, I know now that how the production of nylon is dependent on the caprolactam production, and that caprolactam production is highly dependent on the availability which is cheaply available and readily available. Its cost should not be very high to that of our production of hydroxylamine. So, making that hydroxylamine, that means your NH2OH, is important, therefore, is a typical inorganic compound which is directly related to the production of your nylon. So, we can have the different processes, that means just now in a previous case we have seen that we can use NO for hydrogenation and the production of your hydroxylamine. How you get NO? Because NO is not a typical compound which we get from your atmosphere. Only thing we know that we can get a nitrogen based compound is your typical dinitrogen molecule, N2 molecule. And we have seen that during the production of your ammonia, if we can go for your typical reduction of your ammonia by hydrogenation reaction, we get plenty of your ammonia in your hand for making your urea also. So, that should be your clue that if we can have available NH3, and which is also that NH3, if we can have and if we are able to convert that NH3 to NO, that means the typical oxidation process, which this NH3 should be cheap in your hand and which we all know can be produced from your dinitrogen which is available in air. So, this NO, the production of this NO, that this is the corresponding one for your production of hydroxylamine. One such process is known as Rastrick process. That process making our ammonia to nitric oxide conversion, and then we have in our hand the NO. So, two molecules of NO, if we oxidize it further by 0.5 molar of your O2, that means oxidation with oxygen in presence of ammonium carbonate. So, if we write this simple reaction, what we can see that NO is there and NO is further getting oxidized, forming something in presence of that ammonia and giving you that corresponding nitrite ion formation. That means, we will be getting ammonium nitrite. So, typical ammonium nitrite formation in solution, this is in solution. So, ammonium nitrite will be formed in solution, and that ammonium nitrite along with 2CO2 and H2. So, we are not getting typically the hydroxylamine at that particular point, but we are having now ammonium nitrite. So, this ammonium nitrite which is formed in solution can be utilized for the corresponding conversion, where we use this ammonium nitrite, that means your NH4 NO2 is allowed to react with sulfur dioxide now, because we are having some intention that we can have this sulfur dioxide in our hand, and that sulfur dioxide with ammonia and water. So, you can have this with that of your water. So, this we are giving that we are getting something which is related to that of your ammonia, that means hydroxylamine, and sulfur dioxide is supplied, that is we can have to have the corresponding sulfate salt. So, what we get as the intermediate one is forming as HON and SO3 NH4 type of thing. So, this particular production is directly related to the reaction of your nitrite, your sulfur dioxide and ammonia. So, this is our intermediate now, and this particular intermediate, if we can go, that means the formal reaction with these two molecule of this can be hydrolyzed. So, hydrolyzed in water. So, is basically a water hydrolysis, as we write water in square bracket, at about 100 degrees centigrade. So, at about 100 degrees centigrade, what we can have, this particular one getting hydrolyzed, giving you NH3 OH, twice of this, because sulfate is having a charge of 2 negative charge. So, what we are having now, therefore, that we already seen that this is your thing, this is your hydroxylamine. So, when this particular one proton is getting, this is getting protonated, so we get NH3OH. So, if we have this NH, this will have the charge. That means, if it is further protonated like ammonia, gives you ammonium ion. So, hydroxylamine give you the corresponding hydroxylammonium ion. So, this is your hydroxyl ammonium sulfate. Hydroxyl ammonium sulfate, what we can produce in our hand. Along with that, we can have also ammonium sulfate and ammonium hydrogen sulfate, HSO4. So, these are the side products that we should be also be carefully controlled, such that we get a production of these having a concentration of 70 gram per liter. So, we will be able to produce a 70 gram per liter of that compound from this particular very simple reaction. So, this particular one is a very important one where we get this, because this particular pathway for the formation of this one, that means the formation of this oxidation, and that oxidation giving us the corresponding nitric oxide. So, if we can go also a related process, which is the process number 2, which is a NO reduction process. NO reduction process, what we get is therefore that in the first step what we can have, ammonia again can be oxidized by 2.5 O2 giving 2 NO. These reactions are mostly balanced. Whenever you try to write any reaction, you try to balance it such that you can have the corresponding idea in your mind that how you can go for the atom balance, such as your atom economy. That means whatever side product is forming is here, you see that only water is forming. So, this is your first step of reaction. So, first step is giving you NO in your hand, and in the second step what will you do? As we have seen that it is NO reduction, and we have already seen that how we convert NO to NH to OH, that I told you from the very beginning that you have to add several number of hydrogens on it, hydrogen atoms, addition of hydrogens. So, 3 hydrogen atoms if you add on NO, we will get NH2OH. There is a very simple reaction. Forget about your corresponding configuration, how the bonds are there, how many bonds are there, and what are those different bonds you can have. So, this particular NO, so this NO basically then is react with that of your hydrogen. That means their hydrogen gas in presence of your sulfuric acid, because all the time we are using this sulfuric acid because we are trying to get is or isolate it as the corresponding sulfate salt. So, we will take the help of a catalyst for this hydrogenation reaction utilizing hydrogen as the elemental hydrogen or hydrogen gas. So, the platinum as the catalyst, earlier we have seen that the platinum charcoal bed is also useful. So, this particular case the platinum, again this platinum on C, that means on charcoal bed, or sometime we use the platinum as the corresponding one for the formation of this, and that gives rise to a different process which is known industrially also, inventa process. So, you see that one industrial people or the industry is utilizing one particular catalyst, and the second or the third one is changing only the catalyst, but they are simply using the same process of reactions, but they patent it, they go for its corresponding copyright for that particular one, because the palladium catalyst, when we can use it instead of a platinum catalyst, it can have certain advantages, particularly its cost effectiveness. As a low price you can produce the material, or the time consumed for that particular reaction is also less, and the corresponding yield for the reaction can also be higher. So, modification in terms of the catalyst, which is a very huge area for the development of the different catalysts for these industrial processes, are still very interesting area of research and development. So, if we just simply change one particular catalyst to other, you can change the typical process and you can go for the corresponding changing or utilization of this particular process for making that particular molecule. So, this particular one giving you that particular hydroxylamine sulfate. So, you have NH3OH all 2SO4, this hydroxylamine sulfate, and there we can have certain side reactions also. So, this can have certain side reactions such as we should also be very much careful that you can have ammonia production, because we are talking about the reduction of NO. So, you can have the ammonia production over there. So, this particular thing can be taken care of through a particular process we call that chemical engineers do basically call it as a process control. So, we should go for process control, how you can change the particular chemical process for the production of this particular molecule. So, we can have that hydrogen what we are taking, that means the use of your hydrogen at a particular pressure. So, if you use a high hydrogen pressure, you can optimize or you can increase the corresponding rate of production or corresponding yield of that particular production of that material. And the low hydrogen ion concentration, it can have also thermodynamic implications, because the heat of the reactions and all these things, if we can go for detailed calculations of these things. So, these are the parameters, standard parameters, what can come out from this particular process control for this particular reaction, and obviously the low temperature. So, these three things if we can control, we can utilize a very good amount of production of your corresponding hydroxyl ammonium sulfate. Next, we will just see that how we can utilize the third step. The third step is the nitride reduction process. So, as in the first case we have seen that we can use that corresponding formation of the nitrite and ammonium nitrite formation we have seen. So, directly if we take that particular nitrite, because it is readily available, sometimes it is a naturally occurring material, the chili saltpeter we all know, the sodium nitrate or sodium nitrite. So, sodium nitrate or nitrite if you can have in your hand. So, nitrite reduction process can be a very useful process for the production of your hydroxylamine. So, this particular one, starting from your thing that your ammonium nitrite, if we take, which should be reduced by hydrogen, and in presence of other inorganic industrial acid or mineral acid is your phosphoric acid, not sulfuric acid now. So, what we get now is that the formation of these, again you can utilize a catalyst. We can consider that what sort of catalyst we can use. So, what we get therefore, that the NO2 now, instead of NO, now NO2 minus will be reduced by elemental hydrogen or hydrogen gas. So, this will directly be converted to NH3OH, that means your NO2 minus is converted to NH2OH, which is further protonated from the acid of the phosphoric acid, giving rise to NH3OH plus. So, this NH3OH plus is a cation giving the corresponding anionic part of this acid, where if you lose of one of these H plus, so we will remain with H2PO4. So, this particular salt you can have, and that particular salt when you can utilize for this particular one, you can get it as, instead of sulfate salt, you get it as a corresponding phosphate salt. So, hydroxylamine preparation can also be controlled, that means through that particular process, and again is a industrially important process, and that industrially important process what we get is that your this thing that can be stabilized in presence of your phosphate as the corresponding mineral acid source, and that phosphate can be utilized along with your some other compounds, ammonium, what other we can get if you just go for typically look at these things, the typical balance of this thing, that you have this ammonium ions group available. So, ammonium dihydrogen phosphate H2PO4 is also forming plus water molecules. So, this particular one, so we can have this particular catalyst in your hand. So, again this catalyst is your corresponding metal based catalyst and not all other metal ions, but some precious metal ion catalyst or metal catalyst, not ion, precious metal catalyst can be utilized. So, directly the industry people, they are very happy that if we can make these without going for its isolation, because if you go for isolation you have to think of its packaging and selling in the market. But if this can be utilized for some other production of other material, people can utilize this particular one in situ whatever is formed. So, in situ production of this particular phosphate salt of your hydroxylamine can be utilized by through trapping of cyclohexane. So, this cyclohexane can be utilized, as we have seen that you can have this cyclohexane, as we all know that cyclohexane is this one, is the benzene ring, this is the corresponding benzene one, and it is OH is the phenol. So, this, if we can reduce it to this cyclohexane, you get. So, this cyclohexane can be utilized for giving you the corresponding oxime of this particular CO function. So, we get cyclohexane oxime, which is again we will see that for the production of nylon, this cyclohexane molecule will be very useful, that we will see afterwards. So, we have seen in this particular class that how we can get this important compound like hydroxylamine, and this hydroxylamine how industrially we can prepare and how good they are for making some other value added molecule like cyclohexane oxime. Okay, thank you very much.